Okay, here we are with lesson number 8. Today we're talking about uniform circular motion, which represents the beginning of the end of our unit in mechanics. We've got 2 lessons that talk about objects that are moving in circles. It's 2-dimensional motion, and as we will see, we're going to need to involve some of Newton's laws in 2 dimensions to really get at describing the motion of objects that are moving in circles. So first of all, a small definition. What is uniform circular motion? It's basically motion in a circle at a constant speed. And that's a little bit of a loaded definition because this right here very purposefully talks about a constant speed, not a constant velocity. Because if an object is moving in a circle, its direction is changing. And because its direction is changing constantly, it may be traveling at a constant speed, but it certainly is not traveling at a constant velocity. Its velocity is changing by virtue of the fact that its direction is changing. And because its velocity is changing, we know that there has to be some type of acceleration. And that's what we're going to investigate in this lesson. So let's take a look at what we call centripetal acceleration. Okay, so because motion in a circle always does involve some change in direction, we're going to call that centripetal acceleration. And as it turns out, it's always directed towards the middle of a circle. That's the reason, in fact, that the object moves in a circle, is because it's experiencing some acceleration that's always directed towards the center. Okay? And we're going to prove it by looking at a really close path of the object. But before we do, let's kind of take a look at uniform circular motion, but in a web applet. So this is www.walterfent.de, and this is a great little applet. Don't worry so much about these graphs here, but just look at this diagram. And this little white ball is going to travel in this circular path. It's got a fixed radius. And if we observe what happens as it goes around this circle, we'll notice that, of course, the distance it is from the center, its radius, remains constant. But look at the position vector of x and y. So look at first of all, the x coordinate. And it goes back and forth. And of course, we know that x actually is changing. We also know that y is changing. It's getting lower here in y now. It's getting higher in y. And now it's getting lower, and so on and so forth. So we know that this position vector is changing. Okay? What if we look at the velocity? We've said that, hey, the speed should remain constant, but the components of velocity should change. So let's take a look at this. Well, here we see the length of the speed vector, the length of the velocity vector. The magnitude stays the same, and of course it does. Here's the magnitude of this velocity vector, and at this point it's about 2.51 meters per second. Okay? But look at the x and the y components of the velocity vector. They are changing. Vx and vy are in fact changing. And hey, because velocity changes, we know that there must be an acceleration. And as it turns out, if we investigate this acceleration, we'll notice, hey, these 2 acceleration vectors always point in such a way that we get this acceleration that's directed at the center of the circle. Which is a little bit surprising, because some acceleration pointed towards the center of the circle is really, does that give us the velocity that we saw here? Well, we're going to do a little bit of math in a moment that's going to show us, yeah, in fact, it exactly does give us this velocity. And so why don't we take a look at that now? So here we have a little diagram of a Cartesian coordinate system, and we've got our circle path that's been drawn here for us. Okay, so let's take a look at 2 positions. Let's first of all draw a little horizontal line, and we'll draw V1 up here, and we'll draw V2 down here. So here's V1, and basically what's going to happen is the object is going to move in position from this spot around to this spot, and that's what we're going to analyze. This is an angle theta between here and here. This is some angle theta between here and here. So it's going to move through the same angle, bing, 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 and it's going to move from here to here. Okay, so let's talk about two different things. We're going to look at first the speed, and then we're going to look at the vector. Okay, so we know that the magnitude of this vector, the speed of this, and the speed of this should be the same. Let's find out what those two things are. So because we're talking about a speed, we know that, hey, well, if I know how long it took to get from here to here, and I knew what distance this was, I could find that speed. But how do I find a distance along a curved path? Well, that's arc length. And our formula for arc length, or basically what we know, is that this arc right here, this red arc, which is the distance that this object travels, is given by r times theta. Okay, so the radius of the circle, which is this measure, times whatever angular displacement this takes, which is theta. Okay, so in this case, our speed is equal to r times, hey, what angular displacement does it take going from here to here? Well, it takes 2 of these angle thetas. And we're going to divide it by the time it takes to get there. So really, this is basically, by looking at the speed, this is what we found. Now we're going to flip it around. T is equal to 2r theta over v. We'll use this in a minute, and this will become important in a minute. But really, this is our derivation. We've just kind of flipped it around. All right, so now that we've done that, let's look at the vectors for v1 and v2. Let's look at what they are in our I hat and j hat notation. So we know that the speeds are the same, so the magnitude of the vectors is the same. And here's vector 1. So we basically got v1 cos theta I hat, so that's this horizontal component right here. And we got v1 cos theta j hat, which is, of course, this vector right here. So here we've got v1 cos theta I hat plus v1 sine theta j hat. And that's this little triangle, these components here. We can do the same thing for v2, which is this guy over here. His component will, of course, be v2 cos theta I hat. But then we introduce a negative sign here because, of course, this vector, the j hat component of this vector, v2, is pointed downwards. And so let's take these, because we said that we're interested in finding out this acceleration, and if this acceleration is truly directed towards the center of the circle. And we'll sub it into our first equation, our first kinematics equation for acceleration, v2 minus v1 over t. And we've just found an expression for v2, we've just found an expression for v1, and hey, we have that expression for t. So let's do this. Here it is, v cos theta I hat minus v sine theta j hat. There's v2 with our negative sign. And we subtract from that v1, v cos theta I hat minus v sine theta j hat. The reason that these are negatives is because we have subtracted v1, and then we divide by time. Let's now go and grab that expression for time. First, we can simplify this, because I got v cos theta I hat minus v cos theta I hat. The I hat component of acceleration goes away. And what I'm left with is minus 2v sine theta j hat over time. We can now introduce that equation for time. We can say, oh, minus 2v sine theta j hat over 2r theta times v, divided by v, excuse me. What does this give us? Well, it gives us minus v squared over r times sine theta over theta in the j hat direction. So the negative sign is actually indicating the direction of the acceleration, which is negative j hat. So at the top of the circle, the acceleration of this object is towards the center, right downwards. And basically for small angles of theta, sine theta divided by theta is about equal to 1. So we can say as these angular displacements get smaller and smaller and smaller and smaller, basically sine theta over theta is approximately equal to 1. Don't worry about the proof of why that is. You'll find out later. But basically, we get that the acceleration is equal to minus v squared over r in the j hat direction, downwards in the j hat direction. Now, did that make sense with what we had before? Let's go back to the applet and just refresh our memory. We're going to show acceleration. And so here at the top of the circle, our acceleration should be directed downwards. So let's take a look. Well, here it's directed upwards. Here it's directed inwards. Yeah, at the top of the circle, and we're going to slow-mo it when we get there. As we get closer and closer, bing, right there at this point, the acceleration was directed downwards. And so that result actually makes complete sense. So A is equal to v squared over r. And we could duplicate that derivation for any two velocities along the circumference of the circle. We'd find the exact same thing. Acceleration, when an object is moving in a circle, is always and must always be directed towards the center of the circle. Okay, that's the nature of centripetal acceleration. It always points towards the center of the circular motion. So in terms of then period and frequency, we can also do a quick little derivation, because sometimes it helps to know, oh, well, what's the time for one rotation? And that would be the period t. And we know that the circumference of the circle is equal to 2 pi times r, which is the radius. And so we can say, oh, well then the velocity of one full rotation, which is of course constant, is 2 pi r over t. And we can substitute in for our expression for centripetal acceleration, which is v squared over r. And there we've made the substitution. And we get this equation, that the acceleration is equal to 4 pi squared times the radius of the circle, all divided by the time it takes to complete one revolution squared, the period squared. We can do the same thing for frequency, knowing that, okay, period is just 1 over the frequency. They're inverses of each other. So then acceleration is equal to 4 pi squared times the radius times frequency squared. Now, where are these useful? These will be useful depending on what you're given in your question, in the question that you have. And so basically the most important part of this lesson was knowing that centripetal acceleration, any acceleration for an object that's moving in a circle, is directed towards the center of that circle. So here's a quick example. A race car enters a circular curve of radius 30 meters at a constant speed of 25 meters per second. Determine the car's centripetal acceleration. So this is kind of a little plug and chug here. R is equal to 30 meters. Speed going around this circle is constant. It's 25 meters per second. And so what we can say is that the acceleration that this car is experiencing, which is centripetal, is v squared over r. And so when we square this, we divide by the radius. We get 20.8 meters per second squared. And because it's a vector, we should say it's towards the center of the circular path. Okay? Let's take a look at another example. Space stations can provide artificial gravity by rotating. A space station that's built in the shape of a bicycle wheel has a diameter of 500 meters. How many times each day should the station rotate for an astronaut to experience an acceleration equal to Earth? All right, so this takes a couple more steps. We know that we're talking about rotation. We're talking about uniform circular motion, and we want to experience a pull of gravity, a centripetal acceleration of 9.8 meters per second squared. So we have a diameter of 500 meters, which gives us a radius of 250 meters. We want a centripetal acceleration that's equal to gravity, 9.8 meters per second squared. We'd like to find out how many times each day, so we're kind of looking for the frequency. How many rotations each day should we get to equal this acceleration? And so what we can do is we can simply rearrange and solve for f. And when we do that, we get 0.03151 rotations per second. Well, the question's asking about how many rotations per day. So this is rotations per second, and a quick little conversion will give you the correct answer. Try it on your own. How many rotations will it take in a full day? Unit conversion question. The answer is 2,723 rotations, and it'll give you the same acceleration as Earth.